Hello, everyone. I am so honored to have you all here today, and our Katerina, one of our own, here to give the Yata Memorial Lecture. So let me start with just a little bit about the lecture itself. So the Yata Memorial Lecture in Robotics for the School of Computer Science's Distinguished Lecture Series. Yata was a postdoctoral fellow in the Robotics Institute from 2000 until her untimely death in 2002. After graduating from the University of Tsukuba, working under the guidance of Professor Yuta, she came to the United States. At Carnegie Mellon, she served as a postdoctoral fellow in the Robotics Institute for 3 years under Chuck Thorpe. Teruko's accomplishments in the field of ultrasonic sensing were highly regarded and won her the Best Student Paper Award at the International Conference on Robotics and Automation, or ICRA, in 1999. It was frequently noted, and we always remembered, that the quality of her work was exceeded only by her kindness and thoughtfulness as a friend. Join us in paying tribute to this extraordinary colleague and friend through the most unique and always exciting lecture. And with that, I will introduce Katerina. So Katerina is the JPMorgan Chase Associate Professor in Machine Learning at Carnegie Mellon University. She received her undergraduate diploma from the Electrical and Computer Engineering at the National Technical University of Athens. She received her PhD from the University of Pennsylvania and was a postdoctoral fellow at UC Berkeley and Google Research after that. We're focusing on combining forms of common sense reasoning, such as spatial understanding and 3D scene understanding, with deep visual narrating. The goal of our work is to enable few-shot learning, cumulative learning for perception, action, and language grabbing. Her group develops methods for computer vision, for mobile agents, 2D and 3D visual parsing, 2 and 3D perception, visual language grounding, learning of object dynamics, navigation, and manipulation analysis. Pioneering innovations of her group include 2D to 3D geometry-aware neural networks for 3D understanding and 2D video streams, analogy-forming networks for memory-augmented few-shot visual parsing, and language grounding in 2D and 3D scenes with bottom-up and top-down attention. Her work's been awarded Best PhD Thesis Award, an NSEP Career Award, an AFOSR Young Investigator Award, a Darbrand Young Investigator Award, Google, TRI, Amazon, NVIDIA, UPMC, and Sony Faculty Research Awards. A lot of awards. She was Program Chair for ICLR in 2024. And with that, I'm really honored to have one of our homegrown faculty members here to give this lecture titled Learning World Simulators from Data. And I'll turn it over to Katerina with that.
Thank you. So thank you very much. It's a great pleasure and honor to have the opportunity to present today our work. So the title is Learning World Simulators from Data. Kenneth Craig, back in 1940s, described what that world simulator would do. He mentioned in his book, The Nature of Explanation, that if an organism carries such a small-scale world model, he would be able to query about different actions, the consequences, evaluate our alternatives, run counterfactuals, and in this way behave in a more intelligent way, right? And this quote has been really foundational for today's AI and cognitive science. And essentially what Kenneth Craig is telling us is learn predictive models of the world and use them in look-ahead search so that we learn behaviors. Where are we based on the agenda that he suggested? Well, the first thing that comes in mind is the excellent models from DeepMind, 2017, 18, and 19, AlphaGo, AlphaZero, MuZero, that essentially were able through test time search and train time search to achieve superhuman performance and beat here the Lisa Doll and KGA, the Go champions. So what do these models do? Well, starting from tabula rasa, without any human knowledge, completely unsupervised, they interact with the environment and they learn neural networks, policy networks, and value networks, as well as dynamics of the environment by, at each time step, doing a search, mental search over different actions and their consequences. And the result of that search is that at the root state, you have a better idea of what actions are good and bad. So you have a better policy on your root state, and you distill the results of this search back into your policy neural network. So we see the search as a policy improvement operator. So this is an excellent model-based reinforcement learning method, essentially, that delivers great policy networks that if you run them at test time, you'll get this performance on the dotted red line, and the value networks. So now if you take your policy network and value network and again inject them at test time search process and Monte Carlo tree search process at test time, very much the same search that we use at train time, you get much better performance. And the more budget you give in this search process, the better their performance is. So you see, the more time you spend thinking at test time, the better you do in all these domains. All right? And this is all with learned world models. This is a huge achievement of AI, and it very much matches what Kenneth was suggesting. So this is precisely the dream, to have robot agents that they don't just succeed in distribution, but when they're encountered with a new task out of distribution, instead of just failing, they spend more resources, they think harder, and eventually they succeed. So are today's robots there or not? So we'll see. Humans for sure can do that. So think of yourselves when you drive to work, on your daily commute, how little effort you put because you know already the route. Now at the same time, if you need to drive in a new neighborhood, in difficult weather conditions, you get much more tired, but you succeed, right? You never say, oh, guess what, I was really OOD, it didn't work out, right? So we always succeed. So can our robots also succeed? Can they learn to think at test time? So here is an excellent paper. So where are we stuck? So we think that planning and the field of robot planning, the premise of that field is that planning is the step-by-step thinking. By thinking step-by-step, by planning through your actions before acting in the world, you are able to do well in out of distribution. Right? This is the premise. But what this paper says is that we found that if you are in out of distribution situation, a road that you haven't seen, and so on, your model itself, the learned model, fails. And because your model fails, then of course searching over that model also fails. So despite the fact that learning world models is a supervised learning problem, somehow we haven't managed to find the representations that would allow to transfer across domains. And learning world models is today's central problem in AI, and nobody knows what should the representation be, but we all agree that this is a big missing piece. Now, you may say, what about video models? So this is results from Sora. There is a thought that by scaling video generative models that get better by the day, eventually they will operate as these world simulators, and they're going to be universal, because they're going to operate directly from sensory input, okay, directly from pixels, and we'll be able to use to evaluate different actions and allow the models and robots to think at test time. Well, the truth is that right now they have a lot of hallucinations. Hallucinations simply say that they're inaccurate, okay, let alone being slow. And they haven't delivered, essentially, on that robot planning premise. So what if we do something else? So what if instead of predicting pixels, we just think like a game engine or a physics engine? A game engine also generates pixels, and these are videos generated by Genesis. The physics engine I'll describe in a little bit. But the way these pixels are predicted is that first we predict motion of the objects and the particles in that simulated scene. Then we predict camera motion, and then we render everything, and that's how we get pixels. Okay? So, and this idea of going from pixels back to a 3D structure and motion of the video, right, has to do with causality, ideas about causality, because as time goes by, it's not that the time gives birth to new pixels. It's not that you saw these pixels on my back. This is not just created de novo, but rather they existed, and the only thing that happens is just moved. Okay, so the only thing that changes the motion other than the pixel appearance and disappearance that video models learn. So then the question is, shall we pursue this paradigm? Shall we go from an image into just staying in pixel space and labeling pixels and predicting pixels, predicting observations, or shall we try to jump to some representation that is 3D-like and can decompose, essentially go from pixels back to 3D structure and motion of that structure and predict and reason in that space? Okay, and what could that structure be? So we have these two paradigms, and of course we don't know which one is going to win, but the truth is that right now, the very few companies that have vehicles on the road, their representations look more like the second. Right? So the embodied agents that actually are very intelligent, like the vehicles, right, of Waymo vehicle and Tesla vehicle, they do infer these representations from pixels, as opposed to predicting in pixel space. Now, the premise is that in the future, the first paradigm will also deliver, but this is the situation today. So now what I'm going to discuss next is how can we use 3D along with end-to-end learning for end tasks that we care about, like visual language understanding, VQA, vision question answering, and robot control. Okay? Well, back in 2019, when the field of 3D computer vision was suggesting to go from pixels directly to meshes and point clouds, our idea was that what if we use 3D just as an inductive bias of the representation? We're going to go from pixels to 3D feature grids. So it's a three-dimensional grid, X, Y, width, it captures the 3D scene over time. And at every location, at every 3D location, there is a feature vector that describes the appearance and the geometry of that part of the scene. And this is trained end-to-end supervised for the end task of object detection or pose estimation or predict where the vehicle is going to go and so on, as well as self-supervised by predicting, essentially synthesizing views. And because you operate in 3D, it's super easy to use multiple cameras mounted on your embodied agent, looking outwards or looking inwards. And we've done this, for example, for the task of driving and semantic understanding. And here is some results. We have mountain vehicles. They have multiple cameras. This is just one example. And you see that our model does better than previous works. And these type of pipelines are very similar to what today's vehicles use. Okay? They build those 3D feature maps, what Tesla calls is the vector space, end-to-end supervised from end tasks. So back then, when we developed those architectures, they looked very different than architectures operating on 2D images. In 2D images, we had 2D convolutional networks. These had to do these projection operations that were differentiable, and then they had to operate in these 3D feature grids with 3D convolutional networks. Recently, we're trying to ask, how can these 3D aware architectures relate or help today's vision language models? Our 2D VLMs, okay, which essentially are the powers of today's computer vision, right? We don't have object detectors and pose estimators, etc. We just have one model that uses images and language and trying to predict the end task. How is 3D awareness that we injected related to those models? So all today's VLMs, many of them have a very, very specific architecture. A video comes in or an image, and this is broken into patches. And patches are described with feature vectors. And they stay continuous. They don't need to be quantized. So we call those the tokens, okay, from the video tokens. And there are other tokens that are extracted from the instruction. The instruction here is point to Mon Renier, okay? And there can be other instructions, how many cats you see in the image, where should I leave my wallet, and so on and so forth. So these are also tokenized. So you have now language tokens and image tokens, and there are many, many cross-attentions between the two to eventually predict the result token by token in text space. So if we follow this paradigm, we have long videos, okay, they're very long, and you patchify them, and then, every patch has the appearance vector that we just said, and the positional encoding. And that positional encoding is the XY pixel coordinate and the time step of the frame that this patch comes from. And you can very easily see that it's super easy to overwhelm those vision language models with videos. Okay, because there's so much redundancy in video, and videos are long, and they have high frame rate, and this is already poses huge difficulty in today's vision language models. And our question is, can information about camera motion and depth help today's VLMs handle long videos? So here is how we think about it. So once you have a long video, you can estimate the camera motion. In fact, this is what humans do all the time. We always estimate how our head moves. Okay, a big part of the brain is just doing a motion estimation. So once you estimate the camera motion and the depth, then every patch, instead of having a position that is just the pixel coordinate and the time step from the video, has also a 3D position, an XYZ in the scene. And the good thing about those XYZ coordinates is that all patches across all this long video are described in the same position coordinate frame. Okay, while if you just dump them frame by frame, then the patches are really not related. So you capture on those XYZ coordinates the relations, the spatial relations of patches coming from different images. So you can use now those in today's VLM. So here is how it looks like. So we have an image, and of course it's patchified again, but every patch has a 2D positional encoding and a corresponding 3D positional encoding, what you show here in 3D, in yellow. And now what if you just take those patches and feed them to the same language model or language head or object detection head that today's VLMs have? So in this way, the two architectures are super, super close. And this is something that essentially we realize here with Ayush, who is leading this work, that 2D and 3D understanding are very, very similar. The only thing that changes is the positional encoding here that you see that enters into the attention architecture that describes the position of every appearance patch. Okay? And essentially, what you do is just a transformer. And in 3D, those positions describe XYZ coordinates that we just said. In 2D, they describe pixel coordinates and time. And now you can mix and match 2D layers and 3D layers in your architecture. Here we have a model we call ODIN, omnidimensional instance segmentation, that can process both images in the 2D layer, essentially 2D attentions, and RGBD video sequences, long videos where you estimate the camera motion. Okay? And the way you do that is you have your 2D attention layers and you also have 3D attention layers, the yellow layers. The yellow layers use the XYZ coordinates, and the blue layers use the XY pixel coordinates and time. Okay? So in this way, your VLM operates in a very condensed representation and has a much better results than today's, even the latest proprietary model that have difficulty even fitting the video in their context length. So in this way, as you see, you can do both 2D understanding, referential grounding, object detection, and so on from a single image, or from a sequence of images, a video that describe a 3D scene, when the instruction or the question contains information that is dispersed across the scene. So this VLM doesn't have any problem, squeezing information across multiple frames very easily. And these are, of course, very small architectures that we were even able to train in our lab in comparison to really, really huge models that need this incredible capacity to handle the redundancy of videos. And in this way, 3D vision and 2D vision come close. And here we have a state-of-the-art results. I mean, Ayush and Alex and the other courses have state-of-the-art lab, not only Scannet 200, but also in other data sets. And the benefit comes from, rare classes. So basically, we have essentially married 2D pre-training from 2D vision language models with 3D understanding of the scene from methods that estimate camera and depth. Okay? So these are all the same. It's all just a transformer with different positions. So this is very powerful, essentially combination of the two lines of work. The same idea now we're going to use for robot control. Again, the dominant paradigm for robot policies and robot foundation models is just 2D policies that take 2D images and then predict actions in 3D of where the robot gripper should go. But what if we do again the same thing? What if, here is how, a 2D policy looks like, and it's a generative model, meaning it operates like a denoiser as opposed to just one-shot prediction. Generative models have revolutionized robot policies because they can handle multimodality by iteratively denoising trajectory predictions. But, for the sake of what I want to show, this is how, 2D policies operate. They take an image, they featureize it, and then they try to predict 3D robot end-effectors, while 3D policies essentially take feature patches and lift them to 3D, and there they denoise a robot end-effector trajectories. And the key idea is that there is one common 3D space where both the action tokens, which is where is the gripper, and the visual tokens, which is where is the things in the scene, live and contextualize each other to predict the robot trajectories. So the method is as follows. You take an image, you featureize again with a 2D backbone, and you use the depth to lift those in 3D, and you have a 3D feature cloud now. And then you can also merge other camera views if you have available. And this is extremely easy because we operate in 3D. And then you essentially denoise those robot trajectories. And the very important key is that because we don't want the center of the coordinate frame where we pick the 0, 0, 0 in our 3D space to affect the inference of our model, the attentions that we operate in this space are relative attentions. Okay, they only depend on relative arrangements of two tokens as opposed to their absolute 3D XYZ coordinates. So absolute 3D is not entering anywhere in this architecture. And you see here predictions of those trajectories, and you see here predictions of those key poses. And I show 60 samples of the model that concentrate over those three modes, because when we collected demonstrations of that, essentially of that task, you know, the student sometimes picked up the green grape, and sometimes the red grape, and sometimes the black grape. So, you know, you see how, you know, our diffusion policy, 3D diffusion policy is able to capture the modes accurately without hallucinating new modes and without dropping modes. So 3D diffuser actor is at the top of the benchmarks and, you know, has been adopted by many labs as the head of their policies. And through ablations, we show that it does well because of, you know, 3D versus 2D in apples-apples comparison, 3D does much better than 2D, and relative attentions help. And you can do the same thing from a single camera. You don't need multi-camera input, okay? So 3D reasoning can also happen from a single view. And we have extended this method to bimanual manipulation, and again, without changing at all the architecture, you get state-of-the-art results of how, you know, your two grippers need to move in that joint 3D space. So going forward, we have seen revolution in vision and language through large data sets, and robotics is data starved. Can 3D help in scaling robot data? Okay, so instead of using 3D as inductive bias in our robot models and vision language models, can we use 3D to scale up robot data? And one way to do that is by automating robot training arenas inside the simulation, okay? In the physics engine. We have seen excellent results from Unitree. So here is a very impressive video that everybody knows, and there are other ones with humanoids, etc. All those impressive results are results of sim-to-real learning, learning in simulation and deploying in the real world, zero shot, without any fine-tuning at test time. Why they work so well? Because locomotion is a task where you can get away by keeping your scene rigid at training time. So your simulated scene, no matter how your robot walks, let's say, on the terrain, you can augment the terrain, make it irregular, and so on. You don't need to model the deformations of the terrain as your robot walks around. Now, once you go to manipulation, things are very, very different. There, our robots are fully supervised from human demonstrations, human teleoperation. This is a huge difference. In one case, we let robots play in simulation and essentially learn these nice skills and locomotion, and can adapt at test time to different terrains that they have not even seen at simulation time. Nobody simulates, you may say, nobody can claim that was a cherry-picked result, because in simulation you cannot actually simulate soil that deforms. You cannot simulate mud and so on. Everything is trained in rigid scenes. So it's a huge gap that these policies are able to jump. While once we go to manipulation, everything is, these results are all fully supervised. From large-scale teleoperation, hours and hours of humans teleoperating robots, all right? And this happens across the world, in Asia, in America, and so on. And the reason is that to train manipulation policies, it is not enough for the rigid scene to stay rigid. It needs to move. It needs to react to how the robot essentially moves its grippers and so on. So you really, really need to model the scene accurately. Can we scale up robot demonstrations with teleoperation? I mean, sure we can. I mean, unfortunately, who is we? I mean, we cannot afford to scale. Only few companies can afford that scaling, all right? Only few companies can afford that scaling. So what we want to do is democratize robot learning by essentially staying in simulation. We think simulation is a powerful alternative. There are excellent graphics algorithms that can simulate anything, but each one is staying in the GitHub of every separate author, right? Instead of being together, gathered at one place that robot researchers can use and for their robot learning and sim to real transfer. One thing is, how do we model the physics? A second thing is that even if we have a physics engine, and of course there are incredible efforts and super successful efforts in NVIDIA as well, once we have the physics engine though, how we scale up tasks, how we scale up environments, how we scale up reward modeling, this is a very, very, very big problem, okay? And this is, of course, a bottleneck towards scaling up robot learning. We cannot just afford randomizing a rigid terrain or a bumpy terrain, whatever we do for locomotion. So our idea here is what we call generative simulation. The first thing we tried is, what if we use generative models of language and images to automate asset creation and environment creation and reward function creation, okay, for reinforcement learning. So you can see here some latest examples for image to 3D mesh mapping. This is incredible progress. So the result here is from Hung-Wan 3D, and the other is Cast, and both of them are companies from Asia. And this is just feed-forward image to 3D mesh generation, trained with incredible amount of data. Okay. So essentially, they show how you can really scale up assets. We can really go from any 2D image to a corresponding 3D asset and 3D scene. Now, even before that, 2 years ago, we were able to do that too. We were able to lift any 2D image to a 3D mesh. And the reason we're able to do that is thanks to 2D generative models. Because you can train your 3D differentiable representation so that you have a reprojection error on the view that you see. Now, there is a huge ambiguity because there are many, many missing views. So what do you do there? Well, you just render that 3D representation and make sure that it has high likelihood under a 2D generative model. And specifically, 0 and 2, 3D, that conditions on the view that you see and predicts how the images will look like from different viewpoints. So there is a revolution on 2D to 3D lifting the last 2 years, exactly because of these beautiful and very accurate likelihoods from 2D image generative models. Okay? And we're able to essentially really scale up this technique. And we had promised our Sony collaborators a simulator for cooking, which we're finally able to develop, because now you can any vegetable, take a picture, and make a corresponding 3D asset. And the 3D asset is not just geometry, it's also physics. But the physics properties, we can ask a language model to suggest them. And not only the physics property, but also the size, because the 2D image doesn't have actual size. Okay, so you see here the language model knows that the pumpkin is larger than cauliflower piece and so on. Now, beyond asset development, that as you see, it's doing incredibly well, how we can automate task and reward creation, that's also a very, very difficult problem. Okay, you may have the assets and the environment in your simulator, but you really need to, code up a reward for a relevant task. So our idea in generative simulation was to prompt language models. So we describe the simulation environment. We just put some assets randomly there, and then we say you have access to this API, suggest reasonable tasks that we should pursue, suggest subtasks also, because if these tasks are very long horizon, then RL is going to fail, because we just use off-the-shelf PPO, proximal policy optimization, a very naive model-free method. And then, we also say generate also Python reward functions. Okay, so code up Python reward functions in terms of where the gripper is, where the objects are, and so on. So this is the prompt that we give to GPT. And as you see, it's about microwaves. And with only one example, GPT can generate the corresponding outputs for a very different scene. For example, a scene that has a sanitizer and says, OK, you need to press the sanitizer, and this task has this type of sub-goals, and so on and so forth. And here is a reward function for each one, which then we can feed to reinforcement learning. Something very, very important is this common sense that language models have for breaking the task into subtasks. Without this, RL in simulation would not have worked. As you see here, put the pepper in the drawer can be broken down into those 3 pieces, and each one has a corresponding reward function, and then you do RL for every subtask, and then you link them, and that's how you get the demonstration out. Now, this is what we did with Pushkal. In our Gen2 sim work, and then Yufei and Xian scaled this up even further, and also these beautiful renderings that you see is the Luisa renderer from Genesis, and they were able to do this for tons and tons of tasks and a lot of reward functions, all automated using generative models. Now, have we used those to train robots? This is something that we're working on right now. Now, should we be asking generative models to tell us what to do in our simulation arenas? a more natural thing would be you just watch videos, you watch humans do things, and you just transfer the sub-goals to simulation. And these sub-goals, again, there is a big divide. What should be the form of those sub-goals? And some people at labs argue that the sub-goal should be in, as an image frame, okay, in appearance space, in pixel space. And some labs argue that it should be in motion space, okay, much like what we said with the inversion of a physics engine, that you go back from pixels to motion and 3D arrangements. I think the very big excitement is that now we can go from any monocular video to a corresponding 4D reconstruction, 3D plus time. We can see how things look behind the objects, complete them, estimate their motion also, not only in the visible view, but also in alternative viewpoints. And how we do that? Again, just by extending the previous technique that I described, the reprojection error, as well as generative object-centric priors. Specifically, the right thing to do is you have multiple objects, you segment them, you complete them using object-centric view synthesis, SDS, generative priors essentially, and jointly splat them, jointly reproject them to model their cross-object occlusions. Okay? And as we get more and more data, this type of test time optimization techniques will be distilled into feed-forward models that do this 4D reconstruction in a feed-forward pass. So this is one way to get motion from video using analysis by synthesis, trying to infer the 4D reality that if you render it will give birth to the given video. Another thing that we tried here with Adam Harley is to directly train feed-forward models that can predict motion from videos, motion trajectories. And when this work was developed in 2021, the only thing that was available for tracking points and pixels in videos was linking optical flow fields. So optical flow, for those that don't know, is a motion field that for every pixel has a 2D essentially vector that says where this pixel is going to be in the next frame. So this is just frame by frame tracking. And once there is occlusion, optical flow is not defined. So you cannot really track a pixel beyond occlusions. So our idea there is to completely change that formulation, and instead of operating frame by frame like all previous works, instead we operate into chunks of frame jointly, okay? And essentially jointly estimate the trajectory of a point across multiple time steps. And then we do that is through a feed-forward network, which though runs iteratively. So you initialize the trajectory, for example, assuming there is zero motion of that point. So it's just a straight line that stays in the same place. And essentially, you have a trained network that iteratively updates this trajectory. Okay? This is difficult, though, supervision to obtain. Who can give you where points move from frame to frame? Through occlusions. This is very difficult. Again, we're going to go to simulation. And I think one big contribution of this work is to show that sim-to-real learning for point tracking actually works better than if you try to do self-supervision using video data. So when this paper came out, most people in the field of trying to infer trajectories from videos were doing self-supervision, trying to infer them automatically, and essentially the results were not that great. So our contributions here is you use multiple frames jointly for estimating point tracks. You have an iterative inference, and you train in simulation, essentially sim to real. And then you can track all those points jointly at test time. And there has been multiple follow-ups. It turns out that this point trajectory representation is actually pretty much everywhere for robotics, to use those point tracks as sub-goal representation of what the robot needs to do. And there is a lot of follow-ups, both as improvements of this architecture with CoTracker 1, 2, and 3 from Andrea Vedaldi's lab, as well as using those point tracks for sub-goals of robots. And here on the bottom left is also our follow-up of how do you infer those point tracks, not in 2D space, but rather in persistent 3D geometry, in world space that some 3D method has inferred from the video. So these are how we're going to make assets, and this is how we're going to define rewards by watching video. And I think it's a great opportunity now that point tracking and fine-grained tracking works better than ever. Of course, new architectures for doing this inference end-to-end from videos is also something that we're working on, and I think the community will be working on. Now, yeah, so the agenda of sim-to-real learning is very complex. And you need the physics engine and unique automated ways to make assets and rewards and train your robots. And when we started, there were a lot of problems with existing simulators. For example, some were very good for rigid objects, some were very good for deformable objects. The biggest problem of all of them was very, very difficult to use. It's difficult to use. So here, for example, you see how many lines you need to write in Isaac Gym to insert a Franka model into the environment. So it is not very modularly written. So what Jan was very excited to do is to rewrite from scratch a physics engine that is much more modular and much more general. So it can handle multiple materials like rigid, deformable, gas, fluid, thin shell objects, and so on, and have all physics solvers written from scratch over Tai Chi, a GPU parallelizable programming language that came out in 2018. And the physics engine has a very nice modular structure and is end-to-end differentiable. The differentiability of rigid meshes is not there in our public version right now, but they're going to be added soon. Another thing that the Xian and the whole team actually put a huge emphasis on is on performance. Essentially, revolution in robot learning came for very, very fast simulators, right? So those locomotion results that you saw were just started coming out in 2020, when Marco Hutter's student was able to cut up a super fast simulator for how the robot interacts with the rigid scene. And of course, now we have the simulators are mainstream. And Genesis also is very, very fast, specifically for piecewise rigid scenes is much faster than the alternatives. And this has to do with the way the collision inference is parallelized into the GPU kernels. Is essentially mostly a big engineering project as opposed to an innovation, technical innovation. And what I got out of this work is oftentimes impact doesn't come from cute ideas, but rather for making tools that the community can use easily. And despite the fact that they're very hard, of course, to push. So this took actually 2 years to develop. Of course, there is also very good rendering engines, such as the Luisa renderer, and you can switch between different rendering engines in one line of code. Here are some results of the physics engine. This is the thin cell object that I described. This is the formable objects. You see the different physics solvers in different environments, and you see how well the rigid object interacts with the deformable object here on that, the rigid, let's say, what is this, meal with the dust coming from the ceiling and so on. And here again is the rigid glass. With fluid and so on, and all the different essentially materials interact very, very smoothly, despite the fact that they are taking care from different solvers. I'm not sure why it's not playing. This slide is not playing. Let's see. So what have we done here? Well, we have done the basic sim-to-real transfer results in robot learning that other people have done. For example, you can train quadrupeds and to do different tricks, much like what you can do in Isaac Gym and other physics engines. This one is fully open sourced, so anybody can use it and build upon it. And this is just the beginning. This is being developed and is going to be improved. And in the second release, there are going to be other features, very important features such as tactile simulation that is not now part of the first release. So what are the takeaways from my talk? I think we're in a very exciting time for 3D and 4D inference directly from pixels. And there are very important questions of how can we marry work from computer vision from 3D vision into today's visual language models and video models so that we can help them understand video better. Are there any lessons to be learned, or this work need to be bypassed? So time will tell. So we discussed how we can use generative models to automate simulation, and we presented the new Genesis physics engine. We said that scaling up robot training arenas is an obvious direction that multiple labs are right now pursuing in 2025. I believe we're going to see incredible progress in this very, very soon. So 2024, we can say, was the learning from teleoperation and learning from demonstration for manipulation. I think now the whole community is going to shift towards sim-to-real learning and learning from video. Simply because we're running out of the number of demonstrations that are available, right? So basically, one of the projects was collecting all possible demonstrations from all academic labs, and this data set, is available, and you need, the results need to be much better from what has been achieved from there. So how can we use video models to improve physics engines and to generate assets and to infer motions of how things need to move in the physics engine? And how can you use renderings from the physics engine to further train generative models? How can you inject more machine learning into the physics engine to make the computations much faster? That's also extremely important. So we see a future where physics engines and machine learning are really hand in hand, both to accelerate the physics simulations, to automatically inject assets and rewards, and then really scale this up and really use this in sim-to-real learning, exactly what we have been doing, as well as to distill results of that rendering engine back to video models. So maybe at test time in 10 years, you don't need any more physics engines. The dream of neural simulation will be achieved. Right now, it is not. Another big missing direction that we're working on, and in fact, Yashi is working on, and he's here, and Kashu, are benchmarking robotics in simulation. So benchmarking has been the driving force behind MLP and computer vision. It is much lacking in robotics. The only thing we have is tweets that come and advertise different results from different companies and labs, and we don't have a clue about what is the actual performance. So we think this is a very, very important direction to be able to have the cycle of improving a robot model. So how to improve the model much has to do with accurately measuring its performance. And the last but not least is about planning for robots. Where is planning sitting? Where is test time thinking and thinking step by step? Where are these things in today's robotics? This is how we started. We started saying that, yes, we don't want from images to stay and by labeling visible pixels and predicting visible pixels. We want to infer the 3D behind the image. And then I show you that, yes, today companies, look, they do that. They're able to get these 3D scenes that you see from the pixel images on the bottom left. But to do this, they had to spend enormous resources into annotating objects, inferring their 3D pose, annotating whether a car is blinking or not, inferring the state of a traffic light, lanes on the road, and all other subtasks that have little to do with, okay, how do you need to steer versus not your car, right? So there is these advocates of end-to-end learning. We only need to put learning on the end task, and the end task is driving in the scene. Why we're even bothering to engineering all those related tasks? Are these tasks real or fake? And in fact, there has been a great talk from Ross Girschik, which is a pioneer in object detection in computer vision, a few months back, saying we need to learn from the field of natural language processing. They spend years on trying to compute good syntactic parsers and semantic parsers and emotion recognition and all these subtasks, but none of them mattered. The only thing that matters is predicting the next word. Okay? Could we be pursuing fake tasks also in computer vision? The fake tasks of detecting objects and their pose estimates, if the end task is just to answer a question? So this is what he put out there, which I think is very provocative and very, very thought-provoking. So my answer to that, which I'm not 100% sure, but this is my answer today, is that language models nowadays can improve by thinking step by step at test time. They can spend test time compute and generate thoughts that help them generate better the end answer. For example, you ask the question, a jungler can jungle 16 balls, half of them are golf, half of them are blue, how many blue balls are there? And old models that didn't reason, that just predicted the answer end-to-end, directly what you care about, didn't get that answer correctly. But if you incentivize the models to think step by step, you get a chain of thought, a sequence of text tokens that operate as stepping stones towards the correct answer. And since then, of course, there has been an incredible, research interest and excitement onto how can we supervise those thought chains. We don't want to have humans writing down what should the thought process be so that the right answer comes correctly out. So because we don't have those supervision, we need to use reinforcement learning to infer those thought chains as stepping stones towards the right answers. And indeed, this is happening and is improving. And here are the thought chains coming from DeepSeek. If you ask the model, do something that will delight me, and only use 7 words. And then the model starts thinking, what is delightful? What concepts shall I combine? How can I make sure I don't go above or beyond the 7 words, and so on? And the question is this the end task? These are all intermediate tasks, intermediate thoughts that lead you to the final answer. So if your final answer is to drive correctly, what should these stepping stones be? Okay? So what would be the equivalent of thinking step by step for sensory-based models, right? For robots and for autonomous vehicles and for embodied agents. How can we, infer those useful stepping stones that will help us to do a test time search, spend more time and get better answers without, though, overwhelming the engineer. We don't want the engineer to do what happens in today's autonomous vehicles and go and annotate all these intermediate tasks, some of which may be important, some of which may not be important. For example, faraway objects, it's okay to neglect. So with these questions, I hope next time we meet, I have more answers to these questions, but this is something that we're very excited about and we're putting a lot of thought into. And I want to close by thanking my collaborators, my students, Ayus, Xian, Nikos, and Chungwei, and Pushkal. They all, and Adam led the work that I recently described. Our postdoc Calais and Yunshuan led the work on video 2,4-D. And our collaborators here also from CMU and Chuangan that co-advised Xian into the physics engine, and all our funding sponsors as well. So thank you very much.
So you have just mentioned you can lift the state space, which is a sensor image, to a high-dimensional 3D space, or exaggerate the key point out of it, such that you have a better representation of the real world. In that sense, you can have a better reasoning capability. On the other hand, you also have this very high-fidelity physics-based simulation, which can infer the states in a very high position. But I feel like there is a gap in between. It's from the vision, it can only tell you some visual clues about your scenes, but the physical properties like the friction, the stiffness of the environment is still missing. I'm wondering what's the right representation from the rich sensor information, such that you can plug that into the very powerful physics backend, such that you can do this online reasoning or reasoning with your physics engine effectively.
Great. So the question is the following. Imagine I want to do test time thinking and planning with an explicit physics engine. How can I go from pixels directly to a simulatable representation that needs to have the correct geometry and needs to have also the correct physics? Correct?
Yeah. What's the right representation for the real world to make sure it captures all the information which related to your downstream tasks?
Right, but you mentioned specifically about the physics engine backend,
yeah.
Right? So just let me answer that. So right now, we go from pixels to whole 3D meshes, right? So in the image, you don't see what's the back part of the object. That's okay, you can just infer it in a feed-forward pass if you have the data, right? So the same way you infer the whole 3D mesh and the vertices and textures of that mesh, you can also infer physics properties for each part of this mesh. So to do that, you need to have the training data in the first place. One obvious way to do that is to do exactly what the geometry people did. They took ready 3D assets, rendered them, got images, and then they trained feed-forward neural models to inverse that process. If we don't have that training data, what we can do is we can use analysis by synthesis, going from a video back to the geometry and physics, so that if you simulate using, for example, the NPM solver, you'll be able to get a video very similar to the input video. And in this way, infer the physics property much slower, but in a way that is not part of your training data. Once you have a paired data set of rendered videos with physics and geometry, you can also do just a feed-forward or that's a type of neural network architecture that can do this inversion directly, much like these beautiful meshes that we got coming out of the 2D images. Yes?
Great talk. Why do you think that we need to use so much of compute to model like friction, damping, and all these things to create a physics engine? Like, let's say I'm opening a drawer. I don't need to know the damping coefficient of the drawer to open it, right? So why should we spend so much time?
That's an excellent question. Opening a drawer is much easier than modeling the drawer, right? But if you model the drawer, then you can have tons of robots of all different morphologies interacting with that drawer. You can augment it, make more different drawers. You can have tons and tons of robots playing with it and practicing in simulation. While with your real drawer, it can only be one real robot interacting with it. We know this is hard. We know it's hard to get right now real robots interacting with the real world. It's easy to get infants interact with the real world, right? And this is easy. It's hard to have tons of robots out there interacting with the real world. There are companies that can afford that. They have hundreds of robots in real world environments, and once they fail, the human goes and, I mean, even those people that can afford it, they still don't do any exploration. They just try. If they fail, the human goes and teleoperates the failure. But because we want supposedly to democratize robot learning so that any lab can learn robot skills, because we know that these companies will not share the skills that they're going to learn. That's why we think that this is a very, very important pathway.
We have time for one or two more questions. In these simulations, do you have to model the robot itself and take everything from the perspective of the robot, or how does that work exactly? Like, if you just model a scene, does it know where the robot's placed in it?
Yes, so once you have a scene, you can put the camera wherever you want. So you may as well put it at the head of the robot, at the wrist of the robot, if you want to learn policies that have also wrist cameras, and wherever your real world morphology, robot morphology is, you can do the analogous thing.
Do you have to model the robot itself in the scene? Or?
Yes, absolutely. You need a robot model. Yeah, but this is easy because there are few robots out there, and there are the models for them are available.
Role of traditional physical theorem, etc., which is in a sense very inaccurate in real world, but yet in that abstracted world it has a tremendous sort of inference capability, so that human thinking can do a lot of things that generate imaginative invention and so forth. This is somewhat philosophical question, so sorry about that.
This is an excellent question. So the question is as follows. The humans are not very good at accurate physics, right? Then they have some sort of a simulator that they can roll out at test time and help them, infer actions and take good decisions. This is what we want as well. This is the neural simulator paradigm. All these 3D models that I shared with you that go into that fuzzy 3D feature space and predict motions, they try to operate like this type of very inaccurate physics simulation. One way I think about it is like a game engine. Game engines are not physically accurate, but they are very good at fooling us, and we feel very happy with that. Chris Atkinson gives the example of we all know what we can swallow and what we cannot swallow, but nobody has an accurate idea of how our throat works, and nobody needs to know about it, right? So I totally agree. This is exactly what we want. We want intuitive physics. And we want to be building those world models of intuitive physics from video that somehow manage to generalize to other environments. Now, the example of AlphaGo that I discussed, and MuZero specifically, that learns the dynamics model of the game of Go, does that. It learns everything in a feature space so that those features are only good at predicting the reward of the game, the value function of the game, and the actions of the game, and is doing excellent about modeling what you need to know to win the game, but not at anything else. The question is, we haven't managed to generalize these models to beyond those games and those simulators. That's the problem.
Can you hear me?
Yes, I can.
So, sort of high-level question. How important do you think interpretability is in terms of applying to these various models we talked about? Because, for example, let's say you use a VLM or an open set object detector in a high-stakes deployment scenario, right? There's definitely failure cases, which are great, which are okay to see in simulations, but in a real-world robot navigation scenario, how much of solving that or getting to 100% accuracy do you think is based on more data and just careful training versus being able to look at the model circuits? So recently Anthropic has some work on mechanistic interpretability for LLMs. How much of that do you think is applicable or even tractable in this robotics realm?
Yeah, so how interpretable our models are, right? This is the idea. Yeah, I mean, there are ways that you can have attribution in those big models. For example, if you have models that have external memory repositories, and you know that for this decision, this and this and this are retrieved, then you know where they found those, let's say, ideas. Now, about specifically these embodied agents we're discussing, autonomous vehicles do have a visualization of what the robot knows about the scene. So you can see whether they're making a mistake. If they see the train passing or not, you can see it right there. Yes, so I think exactly because you need to solve all these subtasks. Okay, supposedly the step-by-step thinking is about, yeah, these the relevant objects, and they have this pose information. I would imagine robots in the future will be able to reason in this way. Oh yeah, these relevant objects. Oh, I think the glasses half full. I need to add some more, and so on and so forth. And then the low-level skill goes and kicks in and tries to do that, and then essentially you will be able to essentially attend to the thinking process of the model.
So just let me ask you quite a high-level questions. So simulations used to be used to test the system, but you're saying that the simulation is going to be used not only to test, but also to develop the system.
Right.
So like users as developers as users, like that's going to be your kind of big picture. If my understanding is correct, so my question is, so I'd like to see your big picture at the end of the day. So the headline of your presentation is learning word simulators from data. So taking these word simulators as black box, I know that you're providing it as open source just from user's perspective. If it's a black box, then what eventually you need to use the simulator, say, for example, data set, you said that it's videos, but still do you think that in the future you need other kind of representations of data set just beyond videos, or your big picture at the end of the day, you just need videos, no, say, annotated lidars, data set, no annotated to the...
You mean to build those large-scale simulated data?
At the end of the day, yes. If I'm a user of your word simulator, what do I need to give the simulator and what I will get from?
I see. So how well we can scale up the data in the data engine right now, in the physics engine, depends on how well we are at isolating objects, lifting them in 3D, estimating their pose, how well we can watch videos that I described and tracking them. Okay, it's because we're going to use this to essentially code up the rewards beyond, of course, pick and place and push that are easy tasks. If you want to do something more complex, like put the straw into the martini glass in the right way, you need to be able to interpret the video of how the human does it accurately. So the more computer vision improves, the more physics engine, enrichment, development and instantiate so much its environments, rewards, and scaling up of the robot training works. So the more we can interpret videos, raw videos, the better we can instantiate environments. I think bypassing completely reality and trying to generate simulation environments just by asking the language model, where shall I put the assets? We did it, and it has some limitations. We couldn't do that for Puring, for example. It requires so much, engineering of the prompt that, I may as well just code up the reward function directly myself as a human engineer. Yeah, but you know, computer vision is improving, and there is this cross-pollination, right? The more we can understand videos, the better we can generate simulation data. And I personally very much believe on training perception in simulation, because our point tracker was trained in simulation. I think that was a big change of paradigm of where do we get your annotations, our annotations. So you can get pose annotations. You can figure out, you know, you have a salad and tomatoes and cheese, and you know exactly who includes whom and where everything extends. You will never be able to get those annotations in a real video. I mean, for autonomous vehicles, things are a little bit more separated. You don't see a lot of bunch of cars on top of each other, so it's easier. But you know, if you go to more entangled domains and cluttered domains, it's hard to annotate. So physics engines can also, you know, give us this very fine grained and expensive annotation.
You guys all join me in thanking Katerina. If you have more questions, I don't know if you have any time, but come on down. Thanks.